recording. Let's go to, okay, so when you attack these stats, I suggest that you have this slide next to you when you get started, especially until you're used to all the different rate conversion factors. So the variable that you should use, that you should consider to convert the rate to different unit basis sets is the K. It is the rate constant. It is not your rate itself. It is that rate constant that we manipulate to change the units. So let's start at the bottom. This is where we start. And we want to, in the end, we want to have, and it's maybe a good exercise if you want to do this for yourselves as well. We want to be able to say, if I have a volumetric rate constant. So the volumetric rate constant in a reactor where you have a solid catalyst in that says what is the rate per volume of the reactor is actually something that is, the volume doesn't, the fact that there's volume doesn't catalyze or change the rate of your reaction. It's the fact that there's stuff in that reactor. So if I now should look at Ki dash, and this is the volumetric rate constant that will give me a rate per reactor volume. What is it equal to? It is equal to Ki dash, and in a packed bed reactor, I need to multiply that by rho bed. So the Ki dash is the per kilogram rate constant, and for a packed bed reactor here, packed bed reactor, I have a different equation than for a CSTR. So for a CSTR, the amount of catalyst that I have in my reactor is the catalyst concentration, but in a packed bed reactor, it is that how much do I have? The kilograms per cubic meter reactor. This in a CSTR, that is a variable that is really a variable. It can change because I can have a CSTR with the same volume with 5 catalyst particles, and I can have a CSTR with the same volume with lots more catalyst particles. So it is a true variable as far as a CSTR is concerned. What you must realize is that rho bed, the bed density in a packed bed, is relatively constant. Okay, so if we have a homogeneous particle size distribution, that value of 0.4 is not really going to change in a packed bed. So in a packed bed, my volumetric rate constant, if I don't change my mass-based rate constant, is also relatively constant. Right, so but that being said, what we could now deduce from that is that my Ki, my volumetric rate constant, is directly proportional to Ki dash and rho bed for a PBR and Ki dash and C cat for a CSTR. So let's now move up in our train here. So if I look at Ki dash, what is it proportional to? And this is now the same for both catalysts, for both reactors. So it's not reactor dependent. So my Ki dash is equal to, and now we introduce this new thing, the Ki double dash. This is the area-based rate constant. What we need to remember when we talk about solid catalysts or that catalyzes our reaction is that the area that's available for catalysis, that is a very important variable for any kind of a catalyst particle. So this gives me the rate per active area of my catalyst particle, right? So this is a per area-based rate constant. And I have to multiply this by that variable that you hopefully encountered when you watched the videos, Am, that gives me the amount of area that I have per kilogram. This Am is for our Goon-like catalyst. It's for our Goon-like catalyst where the active surface area is only on the outside of my catalyst ball. So it's like you've got iron that catalyzes your reactor, and you've got iron balls in your reactor and that they are non-porous, so only the external surface contribute to the catalytically active sites. So now my Am is the same equation for both of my catalyst particles, so that is going to be equal to, and here I've got the Am there, 6 over the particle diameter catalyst density. That catalyst density is the density of that iron balls or whatever you have in your reactor. It's not your packed bed, it's the material of which your catalyst particles are manufactured of. So now, if I now consider Am only for a packed bed reactor for a PBR, and you have to do this in TAT 6.1. For a packed bed reactor, I can relate the catalyst density to the packed bed density, because if I have the packed bed density and I have my porosity, of course I can calculate that catalyst density. So for a packed bed reactor, if I should substitute that in, I should substitute that into my AM equation for a PBR. I have AM is equal to, and now my rho C, 1 over rho C is going to be 1 minus epsilon divided by rho bed. Okay, and that is 6 times that divided by my particle diameter. So that is that equation. So if I substitute that into my volumetric rate equation, my volumetric rate constant equation that says for a packed bed reactor, Ki is equal to Ki dash multiplied by the bed density, and Ki dash is equal to Ki double dash times AM, which is now equal to 6, 1 minus epsilon divided by dP times rho bed, multiplied by rho bed. You will see that the bed density cancel out. This is actually a diameter of the particle. This, for a packed bed reactor, is its AC parameter, which gives me the area of active catalytic sites divided by the volume of my reactor. Area of active sites per volume reactor. So this is AC only for a packed bed reactor. For a CSTR reactor, I cannot change this AM. I must have the rho catalyst there. So in other words, for my CSTR reactor, if I have Ki dash is equal to Ki double dash times AM times C cat. This is AC. And AM for a CSTR, I can only write as 6 over the particle diameter and the catalyst density. Right, so now, last step going upwards is going to the only constant that doesn't change. The only constant that is a true rate constant. And that is your rate constant based on the active site. So Ki triple dash. So we've got our 3 dashes. Single dash per kilogram catalyst. Double dash per active surface area. Triple dash per atom that actually catalyzes the active site. Is it palladium, is it nickel on your catalyst, whatever is present on your catalyst surface. So the Ki triple dash is the only constant, right? So now I can relate my Ki double dash to that parameter and say, right, how does it relate? What is the site density? Site density, and that is something that the catalyst manufacturer can also judge. So why are we doing all this, and how are you going to use this in your TAT? So let me get a new page here so that I've got a clean add a page. There we go. So we want to, for instance, say Ki in a CSTR. What is it proportional to? When will it change? It will change if I change. So let's just start. Ki triple dash times the site density. That gives me Ki double dash. If I now times this with AM, this gives me Ki dash. And if I now times this with C cat, this gives me finally that Ki. So my Ki dash is proportional to all these variables. Okay, this is the only constant. This I can change. What is AM proportional to? AM is proportional to 6 over the particle diameter and the catalyst density. That is in all probability not going to change. Therefore, my Ki, and this is in a CSTR. My Ki in a CSTR is proportional to the Ki triple dash, the site density, 1 over the particle diameter, and the amount of catalyst. This is important to remember when you attack TAT 6.2. So this is important for the CSTR question in TAT 6.2. Right. So if I now want to consider that same proportionality, but for a packed bed reactor like you have in that 6.1. That Ki is also going to be proportional to all those variables, outside, okay, but my AM now needs to be multiplied by row bed, and the row bed is going to cancel out because I can write my AM in terms of 6 over 1 minus epsilon, row bed dB of the catalyst. Okay, so the row bed is going to cancel out there. So Ki in a packed bed reactor is directly proportional to that's a triple dash, the site density, inversely proportional to the particle diameter. Right. Okay, so that is what you need to keep in mind in that 6.1. So in other words, my Ki, the volumetric rate constant, is going to change. Okay, so now let's go into the first order reaction that we encounter in that 6.1. So now, those of you who complained about code and making errors in code, most of these stats you can actually do by hand. However, it is still very useful to use Python as a calculator, right? And to not lose your skills. It's very, for me, it is disconcerting how fast our skills erode if we do not practice it. So please force yourself to keep on using Python for the next few stats, even if you don't have to. Integrate something just for fun, because you want to keep up on your usage of Solve IVP. But for a first order reaction, let me give you a kinetic lesson. DF, volumetric rate. So in that 6.1, we can use the reactor volume that was specified. Please calculate that. And that is equal to R of A. For a first order reaction, if I have no mass transfer, no external mass transfer, the intrinsic rate constant apply, and I have Ca in the bulk that I can use. Right. For a first order reaction in these problems, it is often convenient to analytically integrate that expression like you've done in CKN, I suppose. So if you have dFA, dV, let's say I can write this right, so there's a negative missing, min K, and this is FA naught 1 minus X divided by Q. So because this is now my concentration at any point. So it's FA divided by Q. And I can write this also as FA naught 1 minus X. And if I do my product rule, I end up proving that I've got FA naught minus dx dv is equal to min K FA naught 1 minus X Q. Right, and what is the convenient thing is the FA naughts will cancel out here. So therefore, in 6.3, you do not need the inlet concentration, because for a first order reaction, your rate does not depend that rate equation. The inlet concentration will fall away. So now I've got a very convenient equation that I can separate my variables and I can integrate, and I've got the two negatives will cancel out, and I've got K V over Q, and this is min ln 1 minus X is equal to Ki V over Q. Right, and now for a first order reaction, okay, give me some more space. For a first order reaction, and only for a first order reaction, this applies, and I have now in that 6.1, I've got two X values given. I've got the ideal X given, that's that 90% odd, right? This allows me to calculate that intrinsic rate constant, the volumetric rate constant, the one that is free of external mass transfer effects, okay? So now that I have Ki, I can calculate Ki double dash, because I know Ki is Ki double dash times AC. And I know AC is equal to AM times rho bed. And this is a parameter I can calculate. Okay, so now I have that area-based rate constant that I could calculate. Cool. So now only for a first order reaction, let me do this in red, because if you make a mistake, if you apply this for higher order reactions, I stop marking and I give you a 0. Do you hear me? I stop marking and I give you a 0. It is like applying to fail this course. If you just plug in stuff into equations that you don't know when and why they are applicable, make sure that you go through the videos, that you understand why the following is applicable. So for my real x, so now an x real is given. In other words, if I consider all the resistances that contribute to keeping my reaction back there, I have a KCAC due to external diffusion, and that is the correction factor to give it the volumetric equation, because KC is always KC is always a double dash because it's a flux. It relates to a flux, so it's always an area-based constant. Okay, so then plus my volumetric rate that I've just calculated from the ideal equation. So for a first order reaction, what I can now do is I can use my x real, substitute in that same equation, and I can actually calculate the effect rate constant. Please make sure that you can prove to me why I can apply that K effective. No? It's because I substituted CA surface in terms of the CA block. So now that I've got the K effective, volumetric based, I can do a few things. I can either calculate K effective as the area based one. So K effective, I can calculate the area based one by saying, okay, I know that I have the volumetric one, and I can divide that by AC to give me the area-based one, and then this falls away and I use the area-based one, and this allows me to calculate KC, which is the first question that was asked in that 6.1. Right, okay, let me just do there. And now I change stuff. I change stuff in that reactor, and now you have to use your proportionalities to realize if I change stuff, did I change anything here? Okay, so we're in a packed bed reactor. Did I change anything here in my proportionality chain as far as the rate constant is concerned? So I didn't change that because I have the same active sites. Did I change the site density of the sites on the catalyst? Did I change my catalyst particle diameter? If I change the catalyst particle diameter, I changed my Ki double dash, because the Ki double dash, I changed my Ki dash. So, and because I changed Ki dash, I also changed the volumetric rate constant. So, this is the approach that you have to take for basically all the TUTs in TUT 6, is applying these prorations in order to solve for K's, to see how they change. In some instances, it might feel as if you do not have enough information. But remember, when we prorate, if I, for instance, want to use that equation, the Ki, so I have Ki scenario 1, divided by Ki scenario 2, okay, equals, then it becomes an equal sign. It's Ki triple dash, site loading, AM1, and row bed 1, divided by Ki triple dash, L site, scenario 2, scenario 1, scenario AM2, row bed, scenario 2. All the stuff that I may not know will just cancel out. Okay, so the bed densities will cancel out. If the AMs change, their proportionality remains, and then you have to remember this is now a 1 over dP1, and this is a 1 over dP2. Site density stayed the same, or it changes, and that is the way you can calculate from a known volumetric rate constant. I can calculate an unknown one at a different scenario. Okay, right, so let's check out some questions. Stop sharing. Question. Okay, yes, it should be. Okay, does Ki change when L change? Double dash, let me just get a whiteboard to write on. Share a blank there. Ki triple dash only changes when the catalyst manufacturer Ki triple dash. Changes when the catalyst manufacturer does something to your catalyst. It has got nothing, absolutely nothing to do with the reactor type that you are investigating. So it's got nothing, no relationship, Ki triple dash. No relationship to the area of your reactor or densities in your reactor. The same goes for Ki double dash. It's got nothing to do with the shape of your reactor. The only right parameter that depends on how does my reactor look is in a CSTR, it's the volumetric rate constant. And to a certain extent, if I do have a porosity change in a packed bed reactor, so that my bed density changes in a PBR. So the volumetric rate constant, the one that talks about in this volume of my reactor, how much catalyst do I fit in? Okay, so let me just check if I've got more questions. Doesn't CCAT remain constant in a CSTR? It depends. In some of the TUTs, for instance, in TUT 6.2, the CCAT remains constant for a single run. So yes, then I added 5 kilograms and it is steady state in that run. But now I do a completely new run 2. And I recharge my reactor and now I add 10 kilograms of catalyst to that same CSTR. So I have the opportunity, so it's not changing in time as I do a specific run, Alex, I think. It changes between two different scenarios where I change the properties in my reactor itself. Okay, so it's not the same run, it is in different catalysts. So I think I've got all the questions handled. Any other questions before I stop the recording and we delve into the TUT? Yes, that is correct. Angela asked, both Ki triple dash and Ki triple dash are only functions of the catalyst material properties, and the answer is correct. If you look at all the variables that affect them, that's a very good summary. That is in fact correct. Let me just clear here, in preparation for our porous catalyst, why not Ki dash? Yes, so of course. Ki dash definitely also. So let's just have there, let's have Ki dash. So Ki dash is equal to Ki double dash times. And then it is also AM for a solid catalyst or SI for the porous catalyst. So definitely that will also depend on the catalyst properties. Yes, Dean, thank you very much for that. It will depend on the catalyst properties. Changes with catalyst diameter. So you can't say, okay, so let's just clarify. Let's just clarify here. I think I am confusing the discussion. We've got two things. We say the reactor itself, the shape of my reactor, come on, okay, so maybe I should share a screen again. This doesn't want to write. So sorry, let me just share the screen again. Share. Think. Okay. So, some new pages. So we've got two discussions here. Is the shape of my reactor, shape of the reactor, or stuff that I do in my reactor can only affect the volumetric rate constant. Okay, but Ki double dash, Ki triple dash, okay, that can only change. This can change if I change. It's a completely new catalyst type. So this is the only one that is really the true rate constant. This one can change if I change the site density, so not the shape of my catalyst particle, right? The shape of the reactor, the CCAT, can only affect the volumetric rate constant. My Ki dash for a solid catalyst is proportional to Ki double dash times AM, and because this one changes with particle diameter, it will change if the catalyst manufacturer changes the catalyst type. If you change particle diameter, it's a different catalyst that you buy. You can buy catalysts in different sizes, in 3 millimeters, in 2 millimeters, and 5 millimeter sizes, for instance. Okay, so be careful. We are going to next week, we're going to start on the porous catalyst, and then this AM becomes SI. And if I change the particle diameter, SI is not a function of the particle diameter. For a sponge, whether I have a big sponge or whether I have a small sponge, the internal surface area remains exactly the same. So just a word of warning. However, KC always only works with AM because KC, it's done its job. Once it reached that external surface, it's klaar. Okay, the internal diffusion processes does not concern KC. So for KC, make a note. I am going to say this again probably 50 times during the next 3 weeks, so you will get bored of me. KC, if I correct it to a mass-based KC value, always the external surface area. It's an external diffusion process. KI, if I correct that from the KI double dash, it is either AM or SI, depending on whether I have a porous catalyst or a solid catalyst particle. Right, let's see if I've got some questions. More questions. Okay, so just some comments. And bright light, so I like that. I'm going to stop the recording for now then, and then I am going to give you an opportunity to ask questions in Slack and interact with your TAs in Slack. And just keep that slide with you and keep your wits about it. Then this work eventually becomes really easy. Okay, like everything in life, except gymnastics.